Our today's speaker, we have the pleasure to have Cosmin Pohoata from IAS telling us something geometric flavor.
Thank you very much, Hong. Thank you for having me. It's a pleasure to speak in the seminar. So indeed, before I begin, I mentioned everything I'll say today will be based on joint work with Dmitrii Zakharov from MIT, and it will be about a recent preprint of ours on the so-called Erdős-Szekeres problem. So let me begin by reminding you or telling you what this problem is, give some background and some motivation, and discuss some of the main questions. So this problem states the following, it goes as follows. If I give you two parameters, little n and little d, what's the smallest integer, big N, such that in every configuration of n points in d-dimensional space in general position, so no d+1 points clustering on the same hyperplane, there exist n points in convex position. So this is an interesting function to evaluate already for small parameters. So it's an old problem, and already the first case that has some content is the case in 2 dimensions in the plane, d equals 2 and n equals 4. So this function evaluates to 5 in this case. In other words, among every 5 points in the plane, no tricolinear, there exists a convex quadrilateral, so 4 points in convex position, and more than that, 5 is the smallest number with this property. The second fact is, of course, in some sense trivial, so it cannot be 4 because you can choose 4 points that are the vertices of a concave quadrilateral. They do not contain any convex quadrilateral, of course. What needs some argument is that among every 5 points, you have 4 in convex position. And this can be done in several ways. You can, for example, draw some pictures and judge based on the convex hull, but perhaps a slightly more entertaining argument goes by recalling the fact that the complete graph on 5 vertices is not planar. So for example, if you just take your 5 points and draw the segments between them, that gives a planar drawing of the complete graph on 5 vertices, and its non-planarity just tells us that 2 of these edges must intersect internally. So if we look at the endpoints of the corresponding edges, we get the convex quadrilateral. In general, for any dimension d, at least 2, the Erdős-Szekeres function evaluates d+2, so the smallest number of points in d-dimensional space to have d+2 points in the convex position is d+3. It could be a fun puzzle to try to generalize this argument using the non-planarity of K5. It's not really that obvious what to do, but of course you don't really need to. One can prove this in easier ways. In the small chance you're seeing this function for the first time, some of you, so it should not be a priori clear at all to begin with that given 2 integers n and d, that there should be some number big N like this in the first place. In other words, it should not be automatically clear that for sufficiently many points in space, you always have n points in convex position for an arbitrary parameter little n, but this is of course nonetheless true, and it was famously established by Erdős and Szekeres in 1935 in a very beautiful paper, also quite an important one for the history of extremal combinatorics in some sense. It's also Erdős's first paper in combinatorics, not his first paper overall. He wrote some number theory papers first, but first paper in combinatorics, and he provided this connection between this geometric function and Ramsey numbers. So he proved the Erdős and Szekeres proved together that for any d at least 2 and n at least 3, this Erdős-Szekeres function is dominated from above by this off-diagonal Ramsey number for d+2 uniform hypergraphs with parameters n and d+3, where this d+3 is the same d+3 from this equality here. And so it's an important connection, not just because it kind of drew this parallel between 2 seemingly different worlds, but also it was an invitation at the time to study hypergraph Ramsey numbers and ask and hopefully answer or come close to understanding quantitatively how large these Ramsey numbers for hypergraphs can be. So this, of course, comes hand in hand with the quantitative problem for this Erdős-Szekeres function. So how good of an estimate is this Ramsey theoretic estimate? And in a few words, it's really not a very good one. So if one takes the best known bounds on these off-diagonal Ramsey numbers, for example, in the case d equals 2, and these are really the best known upper bounds that were not known at the time. It's a fairly recent upper bound that I wrote there, like from 10, 15 years ago, on Fox and Sudakov. So these numbers are known to be bounded by some doubly exponential function and n squared times log n, while on the other hand, this Erdős-Szekeres function is lower bounded from below by an exponential function. So it's fairly easy to see that one can construct sets of exponentially many points that do not contain endpoints in convex position. In particular, I can easily give you a construction with root 2 to the power n points with no convex n-gons in the plane. The construction goes like this. So you start with the favorite picture when n equals 4, a concave quadrilateral. And then what one does, well, you double this configuration in a generic direction. So you pick a generic direction that has nothing to do with these directions that you already see in the picture. And you really double the picture. So in this direction, put a copy of each point. And you keep doing this. As you see already in this case, if I did it correctly, there's no convex hexagon, but you have 8 points. When you keep doing it, the size of the largest convex subset always increases by at most 2, while the configuration doubles in size. So you get the construction of this order here. Erdős and Szekeres, of course, noticed this, and in this original paper themselves were motivated to do better, and they came up with the following idea. They said, well, let's consider this function, also a Ramsey theoretic function, but with a bit more geometric flavor. So for 2 parameters a and b, let f of a b be the smallest integer n, such that for every set of n points in the plane in general position, you have either an a cap or a b cap. So what are these objects? A cup is a convex set, or in particular, let me say an a cup, is a convex set with a points that looks like this. In particular, if you order the points from left to right based on the x-coordinate, and you draw the consecutive segments, the slopes of these consecutive segments are increasing from left to right. A B cap, is a convex set with B vertices that looks like this, like on the right. I'm not sure if you see my cursor, by the way.
We do. Yes.
Someone like to confirm? Okay.
Yes.
Thank you. I'm not sure if the cursor movements will help at all, but I'll try every now and then. So a cap is kind of the opposite. It's a convex set with the B vertices where the slopes of the consecutive segments decrease from left to right. So this is a function. It's somewhat similar in flavor with the Erdős-Szekeres function. Of course, it's related with the Erdős-Szekeres function in an obvious way. If you plug in a equals b equals n, well, this function evaluated at n and n dominates the Erdős-Szekeres function. This is just an observation that cups and caps are convex sets. So if you have one of the two structures from the previous slide with n vertices, then you have n points in convex position. So this is a trivial comparison. But perhaps more amazingly, one can understand very well this function. So not just write down a very good upper bound for it, but in fact an actual equality. So this function, this cap function, is equal with the central binomial coefficient, 2n minus 4 choose n minus 2 plus some 1 outside. Quantity which is of course much smaller than this doubly exponential function from before. It's close to this 4 to the n divided by root n, ignoring constants. So I'd like to say a few things about this equality. It turns out that for every 2 parameters a and b, it holds in greater generality. So this function f of a b, as defined before, it's equal with this binomial coefficient, a plus b minus 4 choose a minus 2 plus 1, which is the beginning of many interesting stories in extremal combinatorics and beyond, I should say. I won't really have time to touch on many of them, maybe on any outside of the ones relevant to this Erdős-Szekeres function. But here's a comment already. Just from the equality, we already have an implicit stronger lower bound for the Erdős-Szekeres function. So if you plug in A equals B equals n over 2, this Erdős-Szekeres function is bounded from below by f of n over 2 simply because if I give you any convex n-gon, no matter how you draw it, well, the top part will have either n over 2 at least n over 2 vertices, or the bottom part will have at least n over 2 vertices. In other words, any convex n-gon will contain a cap or a cup of size at least n over 2. So you have this comparison, and if you believe in the equality, well, this is a central binomial coefficient, but with n over 2 instead of n here. This is this 2 to the n over root n, which is better than the root 2 to the power n from before. Was there a question? Or, can I hear? Okay. No. My bad then. Okay. So I'd like to say still a few more words about this equality in the general setting, because in some sense it's really the engine behind all the developments around this Erdős-Szekeres problem, all the new. So over the years, it gathered the name cups versus cap lemma. What is really the idea behind its original proof? It's really hidden in this picture. If I give you a cap with blue vertices that I put here on the left, and with its endpoint, I start a cup. So with this guy that becomes purple, red, blue, and red. So with red, I draw a cup, starting with the last vertex of the cap. Then, well, there's some tension here happening. So if this cap has size B, and this cup has size A, so there's some tension here. The slopes, as you see, decrease from left to right in the cap. The slopes increase from left to right in the cup. But what happens here in the middle? So does the slope increase when you go from the cap to the cup, or does it decrease? So depending on what happens, the cap or the cap can always be extended by one extra unit. So for instance, in this picture, as you see here, slopes decrease in the cap, and then there's a jump in the other direction. They increase here. So this means that this whole sequence of slopes, starting with this point here now, is increasing. So the cup can be extended by one unit. And this is really enough to establish a very nice recursive inequality in the style of the recursive inequality we learned early for diagonal Ramsey numbers. It's also, of course, an argument due to Erdős and Szekeres, in fact, from the same paper. So it's pretty much in that spirit. So this function, f of AB, is upper bounded by the sum of these two lower complexity functions, f of A minus 1, B plus f of A, B minus 1, from which you subtract 1. And then by induction, it leads to this upper bound, f of AB is bounded by the binomial coefficient plus 1. And as I hinted at already, all these inequalities, in fact, hold with equality. So the recursive inequality on its own holds with equality. It is possible to construct a set of points without A caps and B caps of this size on the right, and this construction for the recursive equality can be used inductively to give a construction that shows the equality for this this function f of AB. So this is the so-called cup versus cap lemma. A quick recap: what was the outcome of this? This gave us this upper bound for the Erdős-Szekeres function. The Erdős-Szekeres function in the plane is upper bounded by 4 to the n divided by root n, and lower bounded by 2 to the n divided by root n. So it's exponential, and we understand to some extent what's the base of the exponents between 2 and 4. Of course, it's not enough. Wasn't enough for Erdős and Szekeres, and this paper of theirs that's really at the beginning of everything. They also made this bold conjecture at the time that, okay, maybe because of the information we have when n equals 4, n equals 5, n equals 6, and this chain of inequalities above, maybe it should be true that this Erdős-Szekeres function in the plane is 2 to the n minus 2 plus 1 precisely, not upper bounded, not lower bounded, exactly equal to this. Of course, sorry, yeah. Is the question?
It's okay. There was a step that I didn't see from the previous argument, but then I think I understand now.
Okay.
Because you need the end of the cup to match up with the start. The end of the cap to match up with the start of the cup, right?
Yes, yes.
But you can guarantee
it's not completely trivial that this implies
Yeah,
recursive
yeah.
inequality. It needs some argument indeed. I don't know if I can say it in a sentence on the spot. We can discuss if you want at the end.
I think I've seen it before, so I remember now how it works. That you look at the set of points which are not the endpoints of the caps, and it should be small. Good. Yeah. Anyway.
Exactly. One judges based on how large the set of right endpoints of caps is. If it's large, something happens. If it's small, something else happens. Excellent. So I was saying they made this conjecture in the original paper that this planar function should be this, but then conveniently 30 years later, they also backed it up with a beautiful construction of a set of this many points, well, 2 to the n minus 2 points without convex n-gons. So improving on this lower bound, showing that in some sense giving life to this conjecture. I won't be able to tell you what this construction is, but based on this construction, it became it's a famous conjecture to show that this equality holds for all n. And it's a tantalizing problem to not just maybe aim towards this equality, but to improve on this chain of inequalities, especially in light of this equality here for this cap function. So since this holds with equality, the equality between f of n comma n function and the central binomial coefficient plus 1. For example, it's already quite tantalizing to try to see if one can, for instance, prove that the Erdős-Szekeres function is dominated by the central binomial coefficient alone without the plus 1. And in fact, this took quite a long time until Chung and Graham established this, and that kind of opened the door to a long series of improvements. That led ultimately with a really nice paper by Andrew Suk in 2016, who showed that in some approximate sense this conjecture holds. In other words, if you start with 2 to the n plus little of n points in the plane in general position, then there are n points in convex position. So he proved an upper bound for this function that is of the form 2 to the n plus some error term in the exponent that's sublinear in it. Not too long after, this was optimized and also slightly generalized by Holmsen, Mojarad, Pak, and Tardos, showing the following error term. So they show that this planar function is upper bound by 2 to the n plus a constant times root n times log of n. And this is really the state of the art on the planar function. Okay, so let me tell you in a few words what's really Suk's main idea. It's really short and simple with the right tools. His main idea was to use the following structural result due to Pohoata and Walter, known as the positive fraction Erdős-Szekeres theorem, which was interesting on its own for its own sake for quite a while. It was firstly established by Barani, and there were several improvements, quantitative improvements on this result, Pak and Solimoji, maybe others. I'll only state the version due to Pohoata and Walter, which was essential for Suk's argument. So it states the following. If I give you a positive integer k that's at least 3, and I give you a set of points x in the plane, that's fairly large. So fairly large meaning it's at least an exponential in k. An exponential that at first glance, it's just bigger than 4 to the k. Of course, it's somewhat dramatically bigger. The condition I wrote here, x is at least to the 40 times k. But think 4 to the k for now. What can one say if the condition is 4 to the k? Well, just from what we learned on the previous slide, we must have a convex k-gon in X. But okay, we have more than 4 to the k points. So from standard arguments, some sampling arguments, if X is a bit larger than 4 to the k, well, we shouldn't expect just one convex k-gon, but several convex k-gon. And then it's a question of, well, can one say more? Can one perhaps understand a little bit how these k-gons cluster? Can one prove a certain structure that these multiple k-gons have? Turns out this is indeed possible. So what Paul and Walter established is that if X is at least to the 40 times k, then there is a convex k-gon P that has this very nice feature that if you extend its sides, its supporting sides, and obtain these triangular sections. So this is the k-gon, extend the triangular section, you get these blue regions. The claim is that there will be some special k-gon P where each of these blue regions contains a good chunk of the original set X, where that means each of them contains a fraction of 1 over to the 40k points from X. In particular, where are all these convex k-gons? Well, if you pick any transversal, any point in the first region, any point in the second, any point in the last, such a collection of k points also forms a convex k-gon. So you have a ton of convex k-gons, one for each such transversal. Okay, so there's this theorem. It existed before. And then how is this useful? Well, if one starts with 2 to the n points rather than 4 to the n points in order to hope to prove something like this, then okay, you cannot find cups and caps of size n in this triangular section, but you can find cups and caps that are perhaps smaller than n, but maybe now you have the hope of combining them. So apply the cup-cap lemma on each triangular section, and there are really essentially two cases. One can argue with the easy combinatorics that either you find two large cups in two consecutive regions that stare at each other through a given vertex. So two red sets, like I indicated here. So cups and an appropriate coordinate system that kind of look at each other. Together in size, they add up to n. Each of them is smaller. And if you find such a thing, they can be merged and you find endpoints in convex position. Or okay, if this does not happen for any pair of consecutive regions, then maybe you find a large collection of Shire caps that don't look at each other, they stare at the floor. But now if they stare at the floor, there's this hope that maybe you can combine them all together from the border. Of course, I'm hiding everything, but with this principle in mind, it's not difficult to complete the proof really in a page or so. So this is really the story in 2 dimensions. I'll now move on to higher dimensions. So what do we know here? We know something. So we know the first bound. The first bound was quite general. It only uses this Ramsey theoretic argument that essentially starts with the observation that to check that endpoints are in convex position in space, all you have to do is check that all the d plus 2 tuples are in convex position. So we have this Ramsey bound, and I didn't even bother to write down quantitatively what information this gives for the function in the dimensions. As you might know already, these bounds on Ramsey numbers tend to get worse the higher you go in uniformity. So something like this is only understood to grow tower type in the uniformity. So this is a function of n that's the tower of exponential, the length of the tower, which is like linear in D or something like that. So very, very poor bound. Okay. So what next? There's this cup-cap argument. However, it's not really clear at all how this generalizes. And in fact, over the years, there have been many attempts to generalize this argument for this problem. And a lot of interesting math emerged in different directions. There are ways to generalize it, but just not to address this problem. But there have been several interesting works with some generalizations of this argument for other problems. I'll only mention names without really getting into specifics. So there are very nice papers of Elias and Matusek, Buk and Matusek, Moshkovitz and Shapira and others. But it's really not clear what to how to extend it to work for this problem off the bat. However, the situation is not all gloomy. So on the other hand, there's a very simple projection argument that somehow completely defies this higher uniformity aspect of the problem. So if you regard this as a function in the dimension instead, as a function of n, it's not too difficult to see that this is a decreasing function. So the d-dimensional Erdős-Szekeres function is upper bound by the d-1 dimensional Erdős-Szekeres function, which is upper bound by the second, the planar Erdős-Szekeres function, which is upper bound by this 2 to the n plus little of n. So what is this argument? It's quite immediate. Well, let's just I'll say some words next to this picture, just in 3D. So consider a set of blue points, which is as many blue points as you need in the plane to find the convex n-gon. So this many points in space. Okay. Project them to some generic plane. You have now this many points in the plane. You can find the convex n-gon there. Here's a convex pentagon out of 9 points in the plane. And then, well, it's not difficult to notice that if you look at the pre-images of these points, the vertices of the convex n-gon in this plane, these blue points must form a convex set in space. And this argument extends, of course, for any choice of dimension. Okay, so there's this very simple argument that's much better than any of these than this Ramsey argument, for example. So this raises a very natural question. Could this d-dimensional function be perhaps much smaller than the two-dimensional function? So this question was studied over the years, and is in some sense not really clear what to expect. Several different and conflicting conjectures have been provided. So let me quickly go through what could be the possible answers, although they're somewhat exhaustive. So I think the first one, I think it was my favorite for a while. Maybe the answer is just no. Maybe this function is not much smaller than the planar function. It's somewhat of a wild guess, but perhaps weird things can happen if the points just cluster around a two-dimensional plane. So it's not really clear how to improve on this projection argument. In fact, really I should say this chain of inequalities has more or less been the best known upper bound for a while for this function up to additive factors. So there are gains that you can do over this projection argument by projecting a bit more cleverly, rather than from infinity, maybe project from a point in the configuration onto a plane that's separating, that gains some additive factor of 1 or something. So there are things like that you can do. Maybe that's it. Okay. What's the second possible answer? Perhaps the answer is yes. Indeed, the d-dimensional function is smaller, but maybe it's not that much smaller. Maybe the answer is still exponential in n. This was formally posed by Morris and Soltan. So they claim that, okay, maybe this Erdős-Szekeres function is of this shape, 2 times n over d in the exponent plus little o of n. So if you plug in d equals 2, you recover the result in the plane. And in fact, they made an even more precise conjecture along the lines of Erdős-Szekeres themselves, saying that perhaps something quite precise could hold that generalizes the precise conjecture in the plane. Perhaps this d-dimensional function is equal with 4 times the d-dimensional function evaluated at n minus d, where you subtract 3. Which one can check quickly that recovers the 2 to the n minus 2 plus 1 conjecture in the plane, and which somewhat surprisingly holds for a non-trivial range of n in terms of d. So of course, one cannot check this beyond a certain linear function in d, but for a non-trivial linear function of parameters, this holds. So it's somewhat tantalizing to disprove this. Okay, there's the third option. Perhaps this Erdős-Szekeres function d dimension drops much more with the dimension. So perhaps the answer is sub-exponential in n. And Furedi made the following prediction that perhaps this function is of the form 2 to the power n raised to 1 over d minus 1, where you multiply this function of n with a constant that depends on the dimension. This is a function that's sub-exponential and in some sense dramatically sub-exponential with the certain power here that depends on the dimension. So this is based on the best known lower bound construction for this problem to Karolyi and Walter, but in some sense it's also not a very clear conjecture to believe in some sense, because this construction, while very nice, it's a generalization of this doubling construction from the plane that I sketched earlier, which already in the plane doesn't seem like the correct type of construction for this problem. So the fact that this could be the best known lower bound construction in the dimension is also more of a speculation than well motivated conjecture. Okay. So this is where we came in. We were very intrigued by the story, and we really went from, I think, one option to another while working on this problem. So with Dmitrii, we show that indeed the last prediction is the one that's closer to the truth, namely the number of points you need in space to ensure that n points are in convex position is sub-exponential in n. So this three-dimensional Erdős-Szekeres function is sub-exponential. It's 2 to the little o of n, or some sublinear function in n there. In particular, because of this trivial chain of inequalities, this comparison that was before, the d-dimensional function is sub-exponential in n for all dimensions that are at least 3. So this in particular confirms this perhaps natural fact that it should be easier somehow to find convex sets in space than it is in the plane. So in higher dimensions, you need substantially fewer points to ensure the presence of a convex set of size n compared to how many you need in the plane. I should say a few things about the little o of n. So it's explicit, it's an effective function. In our preprint, this is a function of the form n divided by 5 times iterated log. We didn't really bother to optimize this to the max in the original form of the argument, but it can be refined to 3 times iterated log, or maybe perhaps even 2 times iterated log with some extra ideas, somewhat orthogonal to the main ideas in the paper. So I won't really mention this unless you're curious. So this is a function that still nonetheless grows sublinearly in n. So it rules out the first two predictions. There's of course still room for the third one, but as I said, it's not really clear, at least to us, what should believe when. What we do believe is I think the right question is whether indeed there is a constant C, absolute constant, for which maybe there's a power saving in the exponent here. So the three-dimensional Erdős-Szekeres function, maybe it's true that it's upper bounded by 2 to the n to the power 1 minus C for this positive C. However, our methods cannot really seem to address this. One would need some new ideas. Okay, so maybe this is a good time to pause. If there are any questions, if not, I'll move on to say some things about the proof. Okay, All is good. I'll say some of the main ideas in the argument. The first main idea is an appropriate version of the cap versus cap lemma that works for our purposes for this Erdős-Szekeres function. In some sense, it's not really the bulletproof generalization of the cap function. There is still room to say some. It's not fully satisfying, but it is in some sense a generalization. So what is the setup? If I give you polytope P, so a polytope I meant. I should have said in 3 dimensions. Yeah. So I'm sorry. What I'm about to state here falls in a somewhat greater generality, but feel free to read D equals 3. So a definition first. If I give you a polytope in 3D, we say that a finite set is a P cap if the following property holds. Each point in Y is separated from the convex hull of P union Y minus the point Y. In other words, so a P cap, what is it? It's a set that looks like this. So here P is the polytope. I apologize for making it round. It's so just this is P. This is the set Y. A P cap is a set where when you add it to P, okay, the union might not automatically be convex. There could be points on this side of P here. But if it's not convex, essentially it's not convex. It doesn't fail to be convex because of Y. So every point of Y here is separated from the convex hull of the rest. That's what the P cap means. A P free set is a set that looks like on the left. So it's a collection of points where every two, if you pick any 2 points in the set and you draw the line through them, the line through them does not intersect P. No matter how you draw the line, it does not intersect P. So what does the R cap lemma on R3 say? If I give you a polytope with a number of E edges in R3 and a set Y that's P free, so a set like that looks like this, and really it's a general setup. So this polytope doesn't have to be bounded; it can be unbounded. In fact, that's quite important. So general polytope. If this P-free set is large enough, so it's larger strictly than this binomial coefficient raised to the number of edges of P, then from the set Y, you can extract a set that looks like this of size at least A. So you can extract a P cap of size A or some convex set of size B that you may not know exactly how it looks like, but you know that it's convex. Okay. So this is not a difficult thing to prove. I won't. But it's not completely straightforward either. I won't really get into detail, but I'll mention at least some perhaps facts that you might already be wondering about. So of course, this binomial coefficient here is the same as the binomial coefficient in the 2D cap lemma. Okay, but this is a setup in R3, and this binomial coefficient also has a power, the number of edges. So the proof is really by projection and multiple projections and iterated application of Dilworth's theorem. Essentially, for each edge of the polytope, one can define an appropriate poset structure on the set Y. And you want to consider a certain projection in the direction of that edge. One has to analyze what it means to have large anti-chains and large chains in that poset, and with iterated Dilworth, we extract the large anti-chain with respect to all of these posets, and we apply cap lemma in that setup. So those words are not necessarily supposed to mean anything. Just some. I wanted to throw in maybe the buzzwords to know what kind of things go into it. What I wanted to mention, however, is how one can hope to use such a thing to get a bound for the 3-dimensional Erdős-Szekeres function. So the goal is the following. It would be really nice if we can find a collection of T polytopes, P1 up to Pt, each with a small number of edges. So a constant number of edges for each. This constant does not depend on n. Okay, and a collection of subsets, Z1, Zt, that are fairly large with respect to x, so polynomially large. Fx is my set of points at the beginning. In R3 with no convex subset of size n. I want to find these polytopes, T of them, small number of edges, and large subsets, such that two things hold. The set Zi is Pi free for each I from 1 up to T. And each set Zi is contained in P sub j for all I different than j. So with such a setup in hand, one could proceed as follows. So if X is our set with no convex subset of size n, and X is large, larger than a binomial coefficient, n plus n over t minus 4, choose n minus 2, raised to some power c prime, such that when you plug in this bound here, the lower bound it generates for each set Zi is a good enough lower bound to apply the cap lemma. So each Zi is Pi free. Okay. And now if X is large enough, namely this constant C prime is chosen such that the product C prime times C is larger than the number of edges here in this big old one. So it's larger than the number of edges in the polytope Pi in particular. Then I'm in this setup. I have a Pi free set that's pretty large, larger than whatever the required thing is. So it means that I can extract a cap, a Pi cap of size at least one of the parameters, n over t, or I get a convex set of size n, the other parameter. But I don't have any convex set of size n by assumption, so I must have the first option. I must have a Pi cap of size at least n over t. But it turns out this cannot happen either. From the second condition, all these nice containments, it's not too difficult to see that, well, okay, if you have this P1 cap Z1 prime, this P2 cap Z2 prime, this T cap ZT prime, well, turns out this union of them is also convex. So you get the convex set of size n just from gluing these T different convex sets of size n over T. So this case cannot happen either. So you cannot really have that X is larger than this binomial coefficient. X must be smaller than this thing. This should be C prime. Apologize. So X must be smaller than this. But now, okay, if I can ensure this setup with some parameter T that grows with n, this number is sub-exponential in n. So that's kind of the plan. Okay, so let me tell you a little bit, give you a flavor of what are these polytopes, what are these sets. Our second main idea is a structural theorem in the spirit of the Pohoata theorem used by Suk. So it states the following. I give you a parameter k, and I give you a set x in R3 in general position, whose size is large depending on k. Before, in the Pohoata result, I was a bit more explicit. I'll be a bit less explicit now, but for the moment, do pretend that this lower bound is 2 to the 40 times k like before. Okay. In this case, we can, if x is a set of size to the 40 times k, and like before, we can ensure k clusters of sizes linear in x, of sizes x divided by 2 to the 40 times k, that are in convex position, or rather they're sorry, not themselves. If you project them to a generic plane, these projections are in convex position. This is, of course, just an immediate application of the Pohoata structural theorem. If I just project the set x to a generic plane, and I just apply the result in that plane, these projections, pi of x1, pi of xk, are really the triangular regions, the points contained in the separate triangular regions. And so in particular, they're in convex position, their pre-images would qualify as sets x1, xk that satisfy this first condition. So this wouldn't be interesting. We need a three-dimensional condition on our clusters x1 up to xk. In particular, we need the following separation property. For every partition of the interval from 1 up to k, so for every partition of the set of numbers from 1 up to k into 4 interval, it doesn't matter what kind of intervals, they can be closed, open, semi-closed, whatever. Any partition you give me, I would like the following two convex halls to be disjoint. The convex hall of the union of the sets coming from I1 and I3 is always disjoint from the convex hall of the union of the sets coming from I2 and I4. So a picture, I thought I had the picture for this. I don't know, I think I deleted it, I'm sorry. It was very, very simple to draw, but I think I'm using a wrong PDF. I'm sorry. Maybe it will appear later. Who knows? Fingers crossed. Maybe I shouldn't look now. Yeah, essentially, I think the picture was something like this. So if you draw the interval from 1 up to k, like as an interval, split it into 4 pieces. Okay, put 2 of the intervals, let's say I1 and I3 above. So put the labels of the intervals I1 and I3 above, and the labels for the intervals, the second one, the fourth one below. So for every such kind of splitting, the convex hall are separated. So the convex hall of the sets corresponding to the things above is separated by a hyperplane, by a plane from the convex hall of the sets below. So again, this is in some sense the main part of the argument. I won't be able to say too much, just again some buzzwords. So like I suggested already, to ensure the first condition is not too difficult, you apply the Paul-Walter theorem for a sufficiently large parameter, larger than the parameter k here that you begin with. So you have the setup in some generic plane and a projection and the pre-images. And then you kind of build up towards the strong separation property for every partition of the interval by first establishing a preliminary separation property using Ham-Sandwich theorem, in fact, repeated application of Ham-Sandwich. And then this preliminary separation is not really enough to ensure the strong separation, but it's somewhat close. So failure of a separation like this is picked up by a lower complexity failure from Haley-type theorems, right? So these are, if you have two convex halls that intersect non-trivially, so the contrapositive, it must be because of 5 sets that intersect, that their corresponding unions intersect. So one wants to take advantage of this, and the way to do it is to apply Ramsey's theorem. A certain application of Ramsey's theorem together with these kind of Haley-type ideas allows one to use this preliminary separation to build up this stronger separation here. Okay, so there's this structural lemma. Okay, so let me maybe describe now how one can use such a thing to get the polytopes P1 up to PT and Z1, the sets Z1 up to ZT from the goal I declared. So suppose I start with the set X in R3, and it's really the set X that has no convex subset of size n, whose size I want to prove it's at its upper bound by 2 to the little of n, and I want to apply this lemma to X with a constant k. So you should think of this k, if you prefer to think in quantitative terms as a parameter that's logarithmic in x for a small number of iterated logs. So something like 2 times 3 times iterated log, let's say. But don't worry too much about that. But it's a constant that depends, grows with n, and that's quite important. You have this structure. So there's this. There are these clusters x1 up to xk with projections in convex position in some generic plane. And if you look at the pre-images, for every way to partition the case sets into 4 intervals, you have some separation going on. Okay. Well, turns out this leads to a very interesting Dilworth coloring of the set of triples in 1 up to k. So for what's special about triples, if I take any triple, J1, J2, J3, so a triple of elements from 1 up to k, well, 3 elements from 1 up to k give you a partition into 4 intervals. And in particular, depending on how you choose those 4 intervals determined by J1, J2, and J3 on 1 up to k to be closed, open, semi-open, semi-closed, whatever, you have different separations ensured by property 2 from the structural result. From those separating planes in the structure theorem, one can cook up 2 very special polytopes for this triple J. For this triple J, I claim there are 2 polytopes, Pj minus and Pj plus, let's call them, with 3 edges, so bounded by just 3 half spaces, such that the following holds. So 2 conditions. Essentially, the conditions are that each polytope contains a fair amount of the sets from x1 up to xk. So 1 polytope, let's say Pj minus, contains the sets corresponding to 2 of the intervals out of the 4. The first one and the third one, let's say. And then the second polytope contains the sets corresponding to the indices in the second and the fourth intervals, chosen to be semi-closed, semi-open in a certain way. So again, a triple gives you partition into 4 intervals of 1 up to k. Write down separation, the separation property for those corresponding partitions. Study them closely. One can hook up 2 polytopes with these containment properties. That's property number 1. And there is a very fun and important property number 2. If you look closely at the first condition, there's no information about the containment of xj2, so the middle guy in the triple J. xj2 is not in Pj minus, and xj2 is not in Pj plus. It's not considered here and here. But there is a condition on xj2. Every line you draw passing through 2 points in xj2 cannot intersect both polytopes at once. Okay, so here's a picture suggesting maybe what I was kind of trying to describe for bullet 1. Essentially, you have these 3 indices. I just wrote down 2 partitions into 4 intervals that they induce. For instance, take the interval here that's so closed at 1, open at J1. This interval here, open at J3. Okay, and now depending on whether you decide to include J2 or not in the left one and on the right one, you have 2 different separations. So things like this that you write down give you allow you to cook up the polytopes. The second picture is a picture for the second property. So what is this property saying? So xj2 kind of looks like this. You have 2 polytopes, Pj minus, Pj plus. They really don't look like this. So they have 3 edges. They're kind of like this, unbounded. But I think for the sake of the argument, this picture will do. But they have at most 3 edges. And now every 2 points you draw here in xj2, the line through them cannot intersect both sets, Pj minus and Pj plus. Just one. Sorry, I cannot hear.
Oh, no, it's all good.
Oh, okay. Okay, so I won't take much longer. Kind of the punchline I want to get to is that the second property of the polytopes defined for this triple J induces a very nice poset structure in XJ2. So this is where the Dilworth coloring will come from. So notice that you can define a poset like this. If I give you 2 points, x and x prime in XJ2, you can say that one is less than the other if x is contained in the union, in the convex hall of Pj minus union x prime. So if x is in this region, bounded by x prime and Pj minus, then you say x is less than x prime. And it's easy to see that this is a poset. Notice chains in this poset are very interesting. So chains would be sequences of points where the line passing through xx prime for every 2 points in a chain will hit Pj minus, like in this picture. But if the line hits Pj minus, then it cannot hit Pj plus from property 2. So in some sense, a chain is a Pj plus free set. An anti-chain is a Pj minus free set. So chains and anti-chains correspond to Pj plus and Pj minus free sets. And by Dilworth's theorem, we know that we have a chain or an anti-chain of size at least root of the set of the size of the poset. So there is some subset Z of XJ2 of size at least root of the size of XJ2, which remember it's a proportion of X. It's one of the clusters, which is Pj minus free or Pj plus free. And you color it red or blue based on, so you color the triple, you color J red or blue based on whether you're in the first case or the second case. So you have a well-defined red-blue coloring of the triples and 1 up to K. Every triple J, I can do this Dilworth. Depending on the outcome, I make it red or make it blue. I apply Ramsey's theorem for this 2 coloring of the triples in 1 up to K. I get a clique of size T in 1 up to K. So I get T indices among my K sets. I get T indices where T grows with K. And remember, K grew with N. So T grows with N. I get a clique where all the triples from that clique, I have the same color, red or blue. In other words, they are all Pj free, Pj minus free, or they're all Pj plus free. If you unwind what this means, well, those corresponding free sets and the corresponding polytopes really are the polytopes from the dream I put forward after describing the cap lemma. So after Ramsey's theorem, we have T sets Z1 up to Zt of size at least root x and polytopes with at most 3 edges, P1 up to Pt, such that we have the containment. Zi is in Pj for 2 different, whenever I is different than J, and Zi is Pi free. And this allows you to finish. If x is large enough, such that this information on the Zi's allows you to find large Pi caps in them. In other words, if x is at least, if x satisfies this inequality, then Zi prime, then Zi must be at least the binomial coefficient raised to the power 3. So 3 is the bound on the number of edges of the polytopes. So you find a Pi cap Zi prime of size at least n over T. You cannot find a convex set of size n because X doesn't have convex sets of size n. So you have the reverse inequality because this would allow you to glue these T different caps of size n over T. And so you get that X is sub-exponential because you have this setup again with the parameter T that grows with n. It's this parameter from this application of Ramsey's theorem for 3 uniform hypergraphs. So it's a poor dependence, but it depends doubly logarithmically or something on this K. Here. Okay, so I'll end here. Hopefully hopefully this gave you a somewhat fair understanding of the main ingredients.
So let's first thank Cosmin for the nice talk. It's very nice result. Yeah. Any questions?